So we're now going to be moving on, now that we've taken a look, and I'm going to draw this because it is so very important here to really kind of understand. We've got our blocks of the periodic table, right? So if I kind of block it out again, we've got our S block, our P block, our D block, and the F block. Really general drawing of the periodic table, but it makes complete sense to me, at least, in that the fact that it's 2, 6, 10, and 14 wide. Okay? Now, again, I'm just building some more, but what we're going to look at here is what we call orbital diagrams and electron configurations. Really some pretty cool stuff. I like this stuff right here. So orbital diagrams and electron configurations. What this basically is a way of, oops, let me get back here, sorry. It's a way of diagramming, or drawing, I guess you could say, diagramming, where electrons are located around the nucleus. And again, you recall that electrons are located around the nucleus. This is a way of diagramming where it is. Come on in. A way of diagramming where it is, and it also can talk about how, in which orbital it is. So in which orbital, and again, I can't remind you enough that we have our SPDF orbitals, SPDF. So our orbital diagrams and electron configurations are going to be a way of doing that. So let's take a look at describing that in just a bit here. The first electron is going to want to go in the lowest energy orbital. So I kind of go back, and if you see my drawing here, you remember the drawing we talked about in terms of energy levels, n equals 1, 2, 3 respectively. And you remember that I talked about electrons going in and around the nucleus, just like if we had a parking lot that had spaces that were designed and specific to the first person that comes in, and then the second, and then when that row of cars gets filled, we come into the second and the third and the fourth, etc. That's going to be exactly the same way electrons fill around the nucleus. So the first one goes in the first energy level, okay? And so since the first energy level only has the 1s, then it makes the most sense that the first electron is going to go into the 1s orbital. Okay, so let's take a look at lowest energy to higher energy orbitals. The lowest energy orbital is the 1s. Now, what's going to be the next lowest, or in other words, if we're going to our increasing energies, there's no more 1s, right? We have the 1s, but then there's no 1p, no 1d, so it goes to the 2s. And the 2s is the next lowest energy orbital. Now we do have a 2p, but the p is the last of the 2s. There is no 2d. You recall that. So 3s would be next, and then 3p. And I know those of you that are thinking fast are already thinking 3d. Let's just hold off for a second. So there's our orders. So if we want to think about where these things are going, we want to know that the s, if I represent with a dash, right? Remember how I represent an orbital with a dash, and we represent electrons. Whoops. We represent electrons with arrows. Our first electron is going to go in that 1s. Okay? And the second will go also in the 1s. And that's because you can fit 2 electrons in the first energy level, because the Pauli exclusion says you can fit 2 in as long as they're opposite spins. All right? So before I move on, I want to show you some rules for looking at electron configurations and orbital diagrams. The first is the Pauli exclusion principle. And the Pauli exclusion principle says that you can have a maximum of 2 electrons, they must have opposite spins. Max 2 electrons, opposite spins. Pauli exclusion. The second is the off-Baugh principle, and that principle says you must start filling orbitals with the lowest energy orbital first, and then you just go to the next energy orbital until you run out of electrons. I'm going to show you all these rules as I build it, but that's the off-Baugh principle. And the fourth rule might be the most confusing. It's called Hund's rule. Hund's rule says you fill equal energy orbitals so that a maximum number of unpaired electrons result. Why that is because even though electrons can spin in opposite directions and create those magnetic fields, they still are all negatively charged and they would rather be apart from each other. So Hund's rule says you want to get electrons so that there's a maximum number of unpaired electrons. So that's kind of the orbital diagram rules. I'm going to get rid of these, and I'm now going to, again, this is high energy, low energy, and then 1s, 2s, 2p, 3s, 3p was where I was at. Now again, I represented the orbitals with dashes. S, the 2s, and again, as I keep going through, the 2s, how many orbitals in the 2s? Well, notice the emphasis, it's a 2s. So there's only one orbital. The 2p, notice the emphasis again on the p. Because it's the 2p, there are 3 orbitals. All p's have 3 orbitals. In the 3s, again, there's only one because it's an s. And then the 3p, there are also 3, again, because not because there's a 3 in front, but because it's a p. So when we get to the D's, we're going to have 5, and when we get to the F's, we're going to have 7. But at least for now, S's all have 1. Doesn't matter if it's the 1, 2, or 3s, and the P's all have 3.